This presentation is delivered by the Stanford Center for Professional Development.
Okay. Well, we have a special today. This robot is going to show you a video. I'm not sure if you're familiar with those cassettes anymore. Do they exist still? So the Puma here is going to start the VCR. Well, it's starting, and there is a video inside. So this video is about a very important aspect of robotics, which is compliant motion. You see the sponge is pushing up, and you see no deflection on the sponge, right? Which means that there is no force applied. Here we are coming to a surface that is unknown, and the robot is sliding over the surface. So it's making contact at different point. If even we remove the whole object, now here is a wavy surface that is being followed just by saying press down and move to the right, cleaning a window without breaking it. It's very important. No. And well, all of this cannot be done without force control and compliant motion control. So you put an error and still you are doing the same task. Dealing with uncertainties requires you to be able to control the compliance. This is linear compliance, but we can also do rotational compliance. So zero moment. When you push to the left or to the right, you will have a zero moment. So if we could see the video back. So here we are creating a strategy to do face-to-face assembly where the contact forces will drive the robot to move about a rotation center here. And that will result into a robust strategy to do face-to-face without any planning of the trajectory. So from any contact point, you rotate, minimizing these moments of contact. This is another example of a peg hole where the forces of contact are driving the motion to rotate and to insert the peg into the hole. These were developed in the late 80s. I mean, here is a very nice example. We are following this racket without any specification, just the contact forces are driving this motion. So force control is very important, not only for compliant motion, but when you do cooperation between multiple robots, it is also the same requirement. You need to be able to control internal forces, otherwise you will break the object. And here is an example of two Pumas cooperating to manipulate a pipe, or I believe we have three Pumas. Oh, actually still with two Pumas, we are moving a large object. And you can imagine now you are doing internal force control and resulting force control to create the compliance to produce that assembly. So you need to control internal forces, and there is a model called the virtual linkage model that we developed to allow us to capture those variables that you have internally. And for the first time, we were able to produce four-arm manipulation. You have three, and you have the driver. And you can see resulting compliant motion and also internal force control to maintain those contact points and to manipulate this object that we call augmented object. All of these issues we will cover in advanced robotics later. So I'm going to stop here. The tape is very long, but let's just give you an idea about the issue of compliance. So let's just take a case of just 1 degree of freedom. You have an inertia, some displacement, and you have a force. And we come to this all the time by decoupling the system. So if we think about the controller f prime to be just a proportional controller, so you have, you're controlling x, y, and z, and you have a kp prime, kp y prime, and kp z prime, right? So what is the behavior? You push here, and you're going to feel some stiffness, right? And this stiffness is going to come from your mass times kp prime. It's the overall stiffness. Now, if I want to do compliance in the z direction, so I would like to push up the robot, and I want the robot to just move with the force I'm pushing with. What can we do? So if I have a very large kp z, it's going to be very stiff, right? If I reduce kp, what is going to happen? If I push, it will restore itself. I push, I reduce it, it will be a stiffness that is lower and lower, and you will basically move in that direction, right? If you make it 0, what's going to happen? I'm sorry?
Doesn't it just stay where?
Well, if it is 0, it is basically, it is free now. That spring is cut. So you move it, it's going to move. So from the control we developed for the position, because we have a control in x, y, and z in task space, at the end effector is stiff in this direction, stiff in that direction. In this direction, if you change kp and make it 0, now it's free. And just by making kp equal to 0, you are going to have those relations. So the first one will be stiff, in the y direction stiff, and here you will just feel the z prime. I mean the z dot, the damping. Okay? So can we create compliance this way? Just compliance, now it is free. But actually what we want to do is not only to create a compliance, we want to control the force, the contact force. So if I'm controlling, pushing the robot, I would like it to maintain 0 force. So when it feels there is any force, it moves away, which means we need feedback. We need a force sensor. And this is really the requirement in order to interact with the environment. Most of the time, actually, you want to apply a specific force on the environment, and that requires control of forces. Here we have only, we just removed the position control from 1 degree of freedom, one direction. So this compliance along the z direction is the first step. We substitute actually this controller in the z direction with a force controller later, and then we are able to control forces in the z direction as we saw earlier, and position is in the other direction. So this is what we call both motion control together with force control. So this kp prime has a very important role in determining the stiffness, but really the closed loop stiffness, remember, you have multiplied kp prime by m hat. So this is your closed loop stiffness. And if you think about it in terms of just the spring aspect, you can see that kx is your stiffness. But now, what is the corresponding stiffness in joint space? You can compute it, because this kx is displacing delta x, and delta x is j delta theta. So your k theta, the stiffness you have in joint space, is your kx with this transformation. So you can even evaluate your corresponding stiffnesses in joint space. Now, for really dealing with the problem of force control, you need to be able to sense the force. And the reason is, if you think about it, let's say I would like to control some F desired. So let's, if we set just the desired force to the, control force to the desired force, we will see that actually the robot is not even moving. And the reason for that is the friction. So if you think about the friction, as long as your force desired is within the breakaway friction, you're not going to move. your force will not get the robot to move beyond that friction. Then you have also continuous column friction, and you have the viscous friction. So it is really difficult to do accurate force control. All the time you are feeling those forces that are coming, so you cannot do it in open loop. So what you need to do, you need to measure your resulting force at the output. So if you apply 1 Newton meter in this case, the output will be 0. And you really need to be able to measure the actual F and form an error between your desired 1 Newton and your force, actual force, and then you can make feedback control. And with, again, then you will be able to do it. So if you have a sensor, then your sensor is going to give you this sensed force, which is the displacement of the sensor. A sensor is essentially a stiffness that you're deforming. It's very stiff, but the delta x is very tiny. So your sensor will give you the information, and now you can see that what you want is to achieve F equal F desired, which means that you can select a controller that feeds forward the desired force and deals with the error and the feedback through a controller that allows you to control this mass that is moving, but in terms of forces. Now, we can then use this relation between x and F and rewrite this equation in terms of force control. So we can take the second derivative of this in terms of forces, and then we will have this stiffness appearing in the equation, and then we close the loop. And once we close the loop, we are going to have the responses we saw on the video. That is, when we push, we will see not only the feed forward, but there will be an error coming from the sensor, and this error will produce torques to move the robot in a way to reduce this error. So if you think about how we can do this, basically you have the relation between forces and displacement. You take the derivatives, and then you design a controller like this with a proportional term, derivative term, and then you are able to have a closed loop that minimizes this. And the response now is in force space for the robot. I'm not expecting you to understand all these details, but essentially force control is going to be a very, very important aspect of robot control. We just dealt with the motion control. The question is how we combine the two, how we get the robot to apply a force in some direction while moving. If you are cleaning a surface, you need to be able to move, to control directions, and also to control the pressure. So you have to combine these two. And the result is a sort of unification of the task control in terms of motion control, force control, merged together. So there are direction of force control and there are direction of motion control. And these depend on, I'm going to skip this, these depend on the relationship between the object you are assembling. So if you have a sphere, and if you want to put the sphere on a contact, you lost a degree of freedom, right? You cannot move in the z direction. You cannot move in that direction. You can still slide on the xy plane, right? So how many degrees of freedom of motion you have now? Imagine the end effector is holding the sphere on the surface. How many degrees of freedom you have? 2? 5. You lost, yes, 2 in position, and then you still do rotations. You still have those rotations. So you lost 1 degree of freedom by this constraint, contact constraint. How many degrees of freedom we lose here? More than 1? 2. We lost the z-axis, and we lost the rotation about the y-axis, this axis. You cannot rotate about this axis. Okay, how many we lost here? So you see, every time you have a different shape, you are going to lose different number of degrees of freedom. Here you lose 3. So what does it mean? It means that we really need to evaluate that space where we can move. But at the same time, did we really lose that degrees of freedom? Because if I'm pushing here or controlling this moment, I still can do it. I can push with 10 Newton, 20 Newton. So the degree of freedom just went to the space of force control. So in those contacts, if you are talking about controlling that variable, the force, then you didn't lose the degree of freedom. It went just into the constrained space, and you can control now that force. And we can now describe the directions and the relationship between the two and separate the spaces. In here, it's very easy. You can say in x and y, there are no rotation about axes x and y. You cannot rotate this about x and y. You can rotate it about z. But in the z direction, you cannot move, but you can move in x and y. So now the space is split into two parts. And to split the space, we go to a description of the space, and we split it through these omega matrices that allow us to project the motion control in some subspace and the force control in another subspace. And in this case, it's very simple. What directions you can control forces here? The z direction. So essentially, the motion control is in the x and y, and the z direction is the complement. If we call omega bar is the subspace for force control. So the result is a unified framework. What we studied so far was sort of this loop. If I have a motion, I can control it, and I can go to J transpose, and I can compensate for centrifugal Coriolis and do this loop. Now what we are doing, we are projecting those controls in their spaces, and we are doing unified control of motion and forces. And because we are controlling everything in the task space, so we have F motion, F forces, we just add them together. We have a total force that we transform into a torque through Jacobian transpose. And that is what is nice now. You unify all the characteristics. So you can see some lambdas and some other things. The lambda is essentially the mass properties. It is your mass matrix, mx. And this is the mass properties that you are using to scale your controller to decouple the system. And this is done also in the force control loop. The result is very interesting because you can decouple the two systems in their own subspaces. And then you can control them properly. So this is a little bit of maybe the beginning of the introduction of advanced topics that we will see. I'm going to continue with this discussion, but you have really to deal with this very important problem. If you want your robot to interact with the world, you need absolutely to be able to control the contact forces. And contact forces doesn't mean only linear forces, but it also means you control moments. And with moment control, you are going to be able to achieve a lot of things. Because in any assembly, you're going to have some error in the relationship between the two. How do you deal with this? How do you deal with the fact that when you are pushing down, you are going to have a moment generated? Well, you can use it to drive. Well, I'm not going to drive it too far, but spill the water. But you can use it to drive this rotation. And this reaction force here will rotate if you select this point as a center, as your operational point. If you push from here, it rotates. This will be fixed. You can fix it by controlling this point. And now you are rotating about this point. And we use this a lot in doing assemblies between objects, because we are able then to cope with the errors and uncertainties that we have. We know to some extent the relationships, but we don't know exactly where things are. So I'm going to continue with the discussion of advanced topics. And this is part of a keynote talk I gave recently. It starts with some really old robots. I don't know if you've seen. Have you seen this robot? Leonardo? Okay, so tell me if you have seen this one. Can you believe this? You have a robot that can draw. 1773. Unbelievable. Actually, there were a whole family of robots that draw, that play music, that can write. At that time, how can you make robots like this? Well,
She is able to play 5 different melodies. To do this, she moves
how do you program this robot? With the technology of the time.
watches her fingers, presses the keys to produce the desired melody.
So basically, you're going to use mechanical devices. And if you want to see the computer that was used, here is the computer. So you have springs, and then you have to drive the motion, and you can see all these sets of designed trajectories on which you are moving the different parts. So the robot is going to write Jacquet automaton. So, well, robotics was around for a long time, right? And really the question was just waiting. It was in our minds. We wanted to build those machines, and the thing was just we didn't have the right technology. And the technology really came much later and brought the first robots that were almost completely industrial robots that were used in this structured plant to perform repeated tasks such in automobile industry and others. Now, today robotics has moved, and we saw at the beginning of the class that robots are now used, or the application of robots is conceived in many domains, and especially we see a lot of robotics today in medical applications, where robots are coming very close to the human, in fact, inside the body of the human. So this is bringing a lot of challenges as we bring robots closer and closer to the human. This is bringing really the real challenge of robotics, because robotics in the industrial setting requires really little from the robot. Once we understood the requirement, precision, repeatability, and the performance and speed and robustness, we can engineer the machine to do that. Here the problem is we need much more intelligence in the robot to deal with many things that are not known in advance. You need to perceive the environment quickly, respond and react to everything that is happening, and you need to be also moving safely. So those challenges bring the perception and sensing issues that we need to deal with in an environment that is unstructured. And this is really a big challenge, and also a good thing for researchers. I mean, without this challenge, in fact, robotics would have become just automation. But having the challenge of unstructured environment is bringing a lot of interesting issues to the research in sensing and perception, in planning and control. Why planning and control is hard here when you have those human-like robots? What is the problem? Well, I mean, in the planning, the world is changing all the time, and maybe something else you wanted to mention?
Multiple inverse kinematic solutions.
Well, the number of degrees of freedom. You have a robot with not 6, 5 anymore. You're talking about many degrees of freedom, and you need to resolve and respond in real time. And you need in those machines to have not just move to a position. You need skills, almost human-like skills. So you are demanding much more. You need to deal with the human-robot interaction, which is going to involve both physical interaction, touching the human and working with the human, but also the communication, the interaction, the cognitive aspect of it. And you need to build those robots, and you need to make sure that they are safe. You need to make sure that they are capable but safe. So a very important theme in this area is the interactivity. of the robot and also the human-friendly design of the robot so that the robot can really be integrated and working with humans. So if we think about this problem and look at the challenges, you can see on the left, you can see a robot you don't want to be next to. I mean, it shows it is a problem. On the right, you can see a robot. You might think, well, it's smaller. It might be safe. But actually, the danger in this robot is hidden inside. It's hidden inside, and we talk about it in class. You remember this. You remember this n square, the inertia of the motor. This is going to be reflected. And when you're going to have an impact force, you're going to really produce a large impact force because you are going to see the inertia of the rotor of the motor. So there were a lot of development in the area of making robots lighter, safer, and one of the most beautiful one is, you can see it on the top, this is the light arm from DLR, sort of the NASA in Germany. They have been working, in fact we had a lot of collaboration with them in designing torque sensors so that we close the loop at each of the joints. But they developed a very nice mechatronic technology that resulted in this very beautiful robot. And now you can have compliance. You can control the robot to be compliant at all the joints. There is still a problem. The fact that the open loop characteristics doesn't have time, makes it that you do not have time to close the loop. And there are still open loop characteristics that will be reflected during impact, which might make the robot dangerous. So perhaps one of the safest way is to use elasticity with the actuator. Then when you have an impact, the elasticity takes the inertia. Well, this is not going to give you the performance. And that is really the problem and the challenge. So if we think about the problem of collision, we see that essentially you have a robot moving at some speed. It has some stiffness, the environment has some stiffness, and when you have a collision, you are going to have an impact force. This typical problem was studied in the automobile industry, and they came up with a criteria called the head injury criteria. The head injury criteria measures that the risk of injury given the impact forces. In fact, if you think about it, in this plane where we are looking at the effective inertias and the stiffness, we can see that a Puma robot is sitting here at almost 90% of risk of serious injury. And the only way you can make it safe is by covering it with almost 20 centimeters of compliant material. So I don't know, I mean, it will be really, really big. So what is the problem? I know we have a lot of mechanical engineers, so they are going to help me now to solve this problem. How can we deal with this problem? Yeah.
Do you need sensors that are more anticipatory? So
well,
less reactive or more?
Well, actually, the sensor idea is really, really good, but I think there is no way you can guarantee. I mean, if you have a robot, you can never guarantee safety that, a passive safety that is not dependent on a computer or dependent on a controller or a sensor. Anything can break. How can I guarantee that whatever happens, this robot is safe? So I need really to go further, not only to think about how I can improve the feedback, how I can, all what we can do with the sensors, skin, and protection of the robot is good, because that is most of the operation. But I want also to make sure that if I have an impact for some reason, something broke in the robot, the controller, the computer, something happened, I need to guarantee that the impact force is below some acceptable amount. So it turned out that a large part of the design comes from the actuation. And you can see it every time. I mean, you are trying to manipulate an object with this end effector. How do you move this end effector. You need links. And everything we were studying was the carrier of this end effector, right? And to actuate your links, you need motors. And because of the motors, your links becomes bigger and bigger. Because you put this motor here to carry this end effector, then you need to carry both with the link with another motor here, and you propagate the weight. So every time you design a robot, you're hitting this problem. How can I squeeze a lighter actuator here? So you put higher gear ratio, but you reflect larger inertia. But essentially, the torque you need here is very critical. So you come up with some specification. You say, I need a 3.7 Newton meter motor with continuous torque. A torque that you can sustain for a long time. Because a motor has a peak torque that could be produced in short time. And if you keep applying it, you will burn your motor. So once you designed your motor, and now you can lift the gravity of the link and the effector and the load and all of that, what do you say? Well, but my robot has to accelerate, has to give me those performances, and now my motor, I will pick my motor to have those characteristics. So I need strength to carry, and I need also the responses, dynamic responses. Well, actually, this is what you need. You need performances, but what you are doing here is you pick a motor, and then you say this motor needs to be as performant as the acceleration I'm going to produce. And this is really not necessary. Because if you think about the problem in the domain of control and the performance you need, the magnitude that you will need at high frequency is much reduced. So in fact, your requirements are you need large torques at low frequency and smaller torque at higher frequency, which means you can design your robot differently. We never think about it, but we can design the robot not with one motor, but with multiple motors for each joint. Like human have multiple muscles actuating, and actually different type of muscles. So you can place a small motor, the structure will be light, very safe, and you put a big motor at the base. You remove the weight. But if you do this, actually this motor will be reflected at the impact force. But I said this motor is only needed at low frequencies. So now I can isolate the motor. When I have an impact force, it will go through this elasticity. So this is the concept we developed in DM2. It's called distributed macro-mini actuation. That really is interesting in the sense that you build a robot that has the capacity of a large robot, but the safety and performance of a smaller one. Well, this concept since went much further, and seeing the performance you can achieve, I mean, it's amazing. You can take the Puma and build a robot like the Puma with 10 times less effective inertia. That is, you reduce your inertia from 35 to 3.5. And that leads to a large reduction in the inertial properties that you see. So I think you don't understand this. Let me show you what I mean with this. Where is my simulator? Anyone saw the Puma simulator somewhere? Ah, right here. Okay, so if we look at the Puma, I'm sorry, if we look at the Puma, we can display the inertial property of the Puma, and you can see like you have small inertia in this direction and large inertia in this direction. In fact, if I move the Puma, you can see that this inertia is changing. We have singularity. You remember the singularity here. And if we look at it, in this direction you cannot move when you come to overhead singularity. And the inertia becomes very, very big. The inertia goes back to a reasonable value in here. So we can take this mass matrix and represent it as the inertial property and describe those properties on the robot. So let's go back to so you understand those inertial property. The green one is what you have now. You reduce your effective inertia by 10 times, and immediately you improve your control performance. So this concept is quite complicated because it requires this elasticity, requires the big motor, requires transmissions to couple it. And we came up with another idea, which is if we want an elastic actuator, why don't we go directly for muscle-like actuators, like in this nice concept? So we started building a robot like this, and the idea in this robot is that you use bones, muscles, and air pressure, so you are bringing the energy through the air, and now you can lift the robot, you can produce the large magnitude of torques needed, and then you add a small motor on the joint, and this motor will allow you to get the dynamics. So combining the two, you get hybrid actuation that essentially leads to a safe robot design. Now the problem with this is how can you manage all these tubes of air that are going to go to the joints and control? Every joint will need two muscles. Well, because I mean you realize you have a large amplifiers, pressure regulators, and you cannot think just I'm going to take all these tubes. You will have a lot of them, and your arm will be very heavy. So the solution to this problem is what? Is we don't want the tubes, so we want to put this on the arm, big. So what do? Well, make it smaller. Now we identified the right problem. Make it smaller, we can have a solution to this problem. And once a graduate student know the problem, they solve it. In fact, it was a piece of cake, just making it smaller, no problem. So making it smaller, now you can distribute it. And by distributing it on the links, you essentially take one line of pressure running through the whole robot. And at each of the joint, you are distributing the pressure regulated to the value you need at that joint. So here is the arm they built. And in fact, this arm was almost like measured after my own arm. So it is really human-like arm with the constraints of a human and not too big. Here are the dimensions. Well, I'm not sure about the torque. And here is the arm. You can hear the air pressure switching and control. So now you can do force control with this. You control the contact forces, and you produce motions with an arm that is yet lighter from the arm that we had before, 3.5. Here we go to 1.5 kilogram. So let's see it. You go from 3.5 to 1.5 kilogram maximum. And you can see on the red response you have the macro robot. Just the macro, the muscle response is very slow. You get almost 0.5 hertz in the closed loop. Whereas with the macro mini, you can go to 35 hertz. Huge, huge improvement. The other thing is by adding this tiny motor, you are improving the control not only of the overall system, but also by thinking about the macro differently and looking at what you are controlling, you can also do a lot of improvement. What we did, we added sensors to measure the tension. The actuation using muscles brings a lot of nonlinearities in the model. But if you use a sensor, you can close a loop and you can improve your control. So just the macro with a sensor goes to 7 hertz. So this is really, really important, always to use sensors where you can. Well, with the group of Mark Katkaski, we are working now on the next prototype that will come probably in a few months. And this prototype is bringing an integration of all these tubes directly inside the structure. So this is going to be a cool arm. This is some of the built parts, and you can see the overall design. So everything is integrated now inside, and outside we have skin to protect in the first impact and also to produce feedback. So you get tactile information about the contact location so you can control better your robot. Okay? So how many orders we have today for this one? Okay, well, please contact us and send. Yes?
Sensors are in the joint or at the extremity or both?
Well, there are sensors on the inside the structure to measure tension on the muscles, but also we have sensors distributed on the skin outside, and that will measure contact with the environment. So when you hit first, you dampen, so you reduce the impact force, and also you measure where you are touching. Okay. Let's move to another aspect of this human-friendly goal and look at the planning and control and look at the human-robot interaction. So let me start with something that we basically developed in the early 90s, and I mentioned, and probably you saw, all of you saw this couple in our lab, Romeo and Juliet, the two platforms that we use to develop and explore the area of human friendly robotics. So here is the video. If we can have the projector please off. So the idea is really not to think about the problem as, well, moving the platform, stopping, manipulating, moving again, stopping, manipulating. It is about how you can combine mobility and manipulation in a way where you are controlling both. So if you're holding an object and you have to move because of an obstacle, you should be able to decouple the two. We call this the task, and this is the posture. And we are able to control the whole robot to achieve a task and also to achieve the posture in a decoupled way. So with this, you can do a lot of things. You can clean the carpet. Open the fridge. Thank you. Make a contact, control the contact force. Oh, this is my shirt. I think it's the only shirt in the world that was ironed by a robot. I should add, it was ironed one time. This is one of the most complex tasks you can imagine. I mean, you can imagine internal forces control, macro-mini actuation, cooperation between the two. All of this, well, there involves a lot of models and things we will be discussing in advanced robotics. Well, this was accomplished and demonstrated at the opening of this building, the Gates building, and in fact, Bill Gates, when he came to the inauguration, he was quite amused with those robots, which you can in fact also use to interact with a human. So my students used to dance with those robots. Here is another example of how you can interact with them by guiding the motion. So the human is is giving the intelligent task of the guidance, and the robot is following. And this is basically, oh, and Alan is dancing. Okay, so by 97, when we accomplished this, if I don't know if you remember, I mentioned by 97, 98, there was the Honda robot that brought the first walking stably machine, and it was remarkable achievement. It dealt with the locomotion aspect, but it didn't really address the problem of manipulation. And since then, we had this challenge to bring together manipulation and mobility in the way we did it for Romeo and Juliet on a more complex robot that involves many degrees of freedom, a branching structure. We're not talking about contact with one end effector. There are many different points you are controlling. You have multi-contact. You have many constraints. You have a lot of things taking place, and you really need to deal with all of these simultaneously and in a coherent fashion. You cannot pull in one direction without really accounting for what is happening in other directions. So the idea now of dealing with this problem through inverse kinematic is crazy, because you have a lot of degrees of freedom. You do not want to commit your final configuration before moving, because there are constraints and joint limits and many things that happens. So the approach that we discussed in class earlier about task-oriented control makes a lot of sense. You pull toward the goal and the configuration emerges. You do not decide it ahead of time. And this approach results into a very simple way of controlling the robot directly in the task space. So in the next 2 minutes, I'll show you how we do this here. But I mean, you can realize there are a lot of details. Let's go to the arm. That's what we studied earlier. You have a force. You have the gradient of the force. How do we apply it? Torque equal transpose F. Okay, very simple. That should work. We said we cannot just do it like this. We need to account for the mass properties. We need to establish the model between acceleration and forces, and by having a good estimate of this model, we can go and correct this, and now we decouple the system and we align the directions to follow the inertial properties. Now the question is, if we go to this problem, how do you deal with all these points? How do you combine? How do you control this while you're controlling this? If you move one arm, everything else is going to move. How do you decouple the motion of the right arm from the left arm while balancing and doing all these things? That is a good idea. Gyroscopes will give you a good sensing. By integrating, you can find the orientation of the body. You can use that information, but how can we deal with this problem of finding the dynamic equations of a system like this and controlling it? Yeah, we want to use energy, but first we need to get a model of the system for this task and that task and the head and the legs. And so we need to extend this operational space control or model not only to find these mass properties, but I want to find all the mass properties and the coupling between them. It's not obvious, but it's very simple. So when you run into a problem like this, just sit down, relax, and just move back. Move back from the problem. Don't go too close to the problem. Move back. What do you see? You go to a higher dimensional space. If you go to a higher dimensional space, everything appears like one point. So if we take this problem, x1, x2, x3, and put them in a higher dimensional space, in that higher dimensional space, there will be a point, a task involving x1, x2, x3, all of these. And we are back to the beginning. Because now, with this, you can find a Jacobian. Once you have a description, you find a Jacobian, you find your mass matrix, mx, or lambda, what I call. And on the diagonal, actually, you have the mass properties at each of the point. And the off diagonal, you have the coupling between them. And now, you're back to this. Beautiful. You have the same model in a higher dimensional space. And now you can use this model to control the system. It's very easy. We use the energy, that is, we use a force of task to control it with J transpose F. But now, suppose I'm controlling the legs and the hands, but I have all this motion that is possible, right? This is the null space motion. This is what we will discuss with redundancy next quarter. And in there, you have to guarantee that your control is consistent, do not interfere with the first control. And to do that, you filter it with n, the null space of the Jacobian. And the result is that you guarantee that there will be zero acceleration coming from the control of the posture. And that means when we move in the posture space, these points will be fixed. And that is very, very important. And once you have this decoupling, then you can control the system in a very effective way. So the control of the whole body is task field to control the task, posture field to control the posture, and the two are decoupled, so you can generate motions without any trajectory. The question is, how can we find those energies? Can we find those criteria? Well, if we are working with horses, maybe we should look at horses. But if we are working with human, we should look human-like robots. We should look at human. How human do it? And this is really a good question. I mean, we already started to be inspired by the human, the way human move, servo their hands, the way they move their body, and we need to see how all of this can be captured through simple mathematical models that we can use to reproduce the motion. So the starting point would be like just motion capture. Capture the motion, and then, well, I'm not going to replay the motion directly, because if I record the motion and replay it, then we cannot generalize. What we are after is not a specific motion. We are after understanding. So if you have a system you want to understand, what do? You shake it enough to find all the behaviors, and to shake, and then you identify it with the model of that system. So you need a model of the system. I mean, it is really interesting. We were working with robots, and now we are working with human model. But human model are essentially articulated body systems. The mass matrix you computed is the same. You can use the same mass matrix. The actuation is different. So for the mass matrix, you can now take the rigid body part, the skeletal model, and now animate it. And this is what you see. In fact, drop it in the gravity field, a pendulum. The idea is, how can we go from the human to the robot, right? And with less degrees of freedom. So we want to see the characteristics of the motion. To see the characteristics of the motion, you need to see the actuation also. You cannot do it without the actuation. So we modeled the muscles, and all of this was done with people who are working in biomechanics, the group of Scott Delp, who provided us with all the data about muscles and the skeletal system and skeletal model. And once you have all of this, you can start doing the study and the analysis, and you start to look at it and try to find what is going on. So to analyze this, where do we start? So we can say, okay, let's start at something very simple. I'm going to give the human a task, which is like to hold some object. And the question is where the posture is going to be. Imagine you are pushing it was very cold in the morning, your car didn't start. You're going to push your car. How do you push the car? You push it this way, or you push it like this? The answer is obvious. Actually, the child, when at birth, didn't know that. So little by little, you learn, and you discover something amazing about the human body, and then you start using it. And what is amazing is in any mechanical structure like this, there is a mechanical advantage. And when you discover the mechanical advantage, you start to using it. So you do not just use the rigid body mechanical advantage, you are also using the way you're actuated and your muscles. The child, when he's moving first, will pull the muscles and it hurts. And you have this feedback, and little by little you start to adjust the motion and move your body correctly. So human, little by little, are learning, discovering a way to minimize the effort produced by the muscle. And this is our speculation. We said there is muscular effort minimization, but it's not always like that. It is, there are also a lot of other constraints, like it's much easier to bring the spoon to the mouth than easier to bring the mouth to the spoon than the spoon to the mouth. And the reason is mom says, this is not polite. You cannot do this. You have to do it this way. So there are a lot of social constraints. There are a lot of other constraints, physical constraints on the system that you need to integrate. But essentially, you are minimizing the effort. And if you say I'm minimizing the effort, it's very important, because now you bring the physiology in the model and you start analyzing the physiology and you look at it. So a robot produces a force by applying a torque J transpose F. All of you now know this, right? A human produces the torque using another Jacobian, L transpose. This is the muscle attachment Jacobian. And these are the muscles. Now, if you think about it, you are really tuned to use this in a way to minimize your muscular effort. But every muscle has a different capacity, bigger muscles, smaller muscles. So you need to account for the capacity of the muscle. So here is our hypothesis. We think humans are adjusting their posture to minimize muscular effort. So there must be an energy. Okay? Okay, now pay attention. We want to find this energy. So the muscle is M. Extension of the muscle, the tension is M. If I'm minimizing the muscle effort, the energy is going to be in M squared, right? But there is the capacity, and what we speculated about is that this energy is weighted for different muscle with their capacity. So here is the energy. Are you already sitting? Okay, are you ready? Want to see it? Okay. Now, if you look inside of this, this is what you see. This captures the following. Captures your task, captures the mechanical advantage of the skeletal system, captures the muscle attachment and the capacity of your muscles. If a muscle is weak, you compensate for it. If a muscle is missing, you're compensating for it, etc., etc. So, in fact, it turned out that our student went to the motion capture lab and we did the analysis, and it's amazing. Actually, I see you sitting comfortably. Why don't you just relax your back and move forward without touching anything with your back? Let's try it. We're going to see if it works also with you. So let's drink a cup of coffee. Don't drink it completely. Just go very close to drinking the coffee. And comfortably, and like you relax. And yeah, let's go. Okay, now look around. Everyone is doing this not like this, not like this. It is like this angle. And this angle corresponds, in fact, to the minimum of this energy. So it is not a coincidence. In fact, if you do this analysis and you increase the weight, this angle goes up. And you can see it here as you move and increase the weight from 0 to 15 pounds, for instance. This is the speculated angle that you will find. You can check it on the body. It makes so much sense. You are discovering how to use this machine, and you are able to use it for the specific task in its optimal way. And it's not only Jacobian, that is, it's not only the skeletal model, it's also the muscle attachment and the way the muscle capacity is distributed. So with this now we can go and simulate and create. So we are doing, I'm not sure if you understand this. Let me, you remember I showed you Standbot. I think I showed you this, right? We saw Standbot. You saw this before, right? Okay, quickly. So we move to the goal, we move to the goal, we move to the goal, and you are able to just track that motion, right? And you remember you can fall, boom, hit the joint limits. All right, so now let's go back to this. So this is what we're doing. We are controlling one point and the body is adjusting through a criteria in the null space, and now you can move it to the robot, not as a trajectory you're copying, but as a criteria that you're applying to the robot. Well, this is the environment we developed that also contain neuromuscular models that can be used to analyze and look at a human. This is a recent work on Tai Chi analysis, and the master here from Beijing is performing a motion that we can record, and then we can analyze the motion, and you can start to see that, well, all these models can produce amazing things, so that essentially you can analyze skills of a human, you can look at the behavior of the human, synthesize it, and in fact, if you record that motion and if you play it back on the physical model of the robot, it will fall over because you need control. You have errors, and unless you control it correctly, it's going to fall. So what we are going to show here is half of the body is following the Tai Chi motion and the other half is controlled, and in fact, you can see that you can achieve those desired half while you're controlling the robot with other behaviors. So all of these are part of the development that is now being implemented on humanoid robotics like Ashimo, and a key aspect of the implementation and the task-oriented control is not only just motion and force control, but how do you deal with constraints? How do you deal with the fact that if you have a joint limit and you're moving and you hit a joint limit, what is going to happen? So this structure of control that I talked about produces a very useful way to apply constraints. Essentially, I mentioned about constraints in terms of attractive forces, repulsive forces. Now, if you have a constraint, it has to take the highest priority. In the structure of task and posture control, we have priority. This task will not interfere with this. So if we know a constraint and we know the Jacobian of that constraint, then we can know the null space of that constraint. Then we can take this whole thing, put it in the null space of that constraint, and then control the constraint. And now the robot is moving, and you can see two different postures because you have a hip limits. Here you are stuck, you cannot reach because of joint limits. Here the body is going to move away to avoid self-collision. So the trajectory is going through the body, and the body will move away automatically by these repulsive forces. Obstacles. So it is very, very important to be able to create those interactive behavior that allow you to avoid collision, but at the same time you need to think about the global path, not only about the local behavior. And well, we have n degrees of freedom. The problem is exponential in the number of degrees of freedom. You have really to deal with a way of connecting the two. And to do that, we developed a concept of we call elastic planning, which essentially connect all the plan, but allows you to deform it in real time. And by deforming this, we are able to change a feasible plan and adapt it to the real environment. And this is an amazing thing, because you are able now to change a trajectory that requires hours of replanning. If you didn't use this, for instance, you will have to replan the whole trajectory with the new obstacles and constraints. At the same time, you are reconstructing, because when you are touching, teleoperating, interacting with surfaces, you need to reconstruct the surface to fit and control your robot. And that means you need to model contact correctly. You need to deal with the contact models also in the control. And this is a very, very interesting result that comes directly from control. You remember when we talked about collision, essentially we are interested in the collision with the multi-body system, but how can you resolve it? Well, people usually remove the joints, resolve the whole free multi-body collision, and then they put the joint, eliminate constraints. But in here, we are going to be able to reduce the problem to this, because we can use the mass matrix in this direction. We can use the effective inertia directly. The collision doesn't care about what humanoid robot you have. You just need to know what mass properties you have at the contact. So with this, we have a very effective algorithm that allows us to simulate and resolve collision in real time. And with the real-time resolution, then you can go and use it in many different things. I believe I showed you this at the beginning of the class, but now you understand what it means. We are able to find the properties in impact forces, and we are able also to deal with this problem of contact and collision. The problem is very difficult, because when you are looking at a humanoid robot, you just push it and it will tip over. It is missing these 6 actuators. It's not connected to the ground. And you spend your time balancing. And if you have any reaction force, it will tip it over. So the question is, how can we move this body while dealing with those constraints? How can you do it? Well, just say it. Say, I need to treat these as constraints. What are your constraints? These normals. Take the Jacobian, take the null space, and take this and put it in. Now you know how to do it, right? Put it in the contact space. And then you are able to bring the two together. And now this motion will be consistent with the constraints, and you can control the forces at the constraints. If you remember in the beginning of the class, we talked about omega and omega bar. This will become your omega bar, and this is your omega in the multi-contact space. So that was really a very important result to allow us to implement behavior with multi-contact and motions, and now distributing the effort between different surfaces that you are touching, moving, balancing, dealing with dynamic skills, etc., etc. So then you can start to build behavior over this. That is now the robot is looking, watching. It is, if there is an obstacle, it will move down. If there are constraints, you are able to deal with the constraints. As it moves, it is automatically generating the right motions to avoid hurting those constraints. And as we are building, we are moving up and up in the structure. So what we really have seen in the class is really the lower level in this system, where we are looking at the execution of the motion controllers, the first controller. But on top of this, you can build behavior that make use of those primitives, and you go up to levels where that now you require more abstraction of the sensory information, your perception. And as you are building a solid foundation, you are going to be able to move higher and higher by integrating also skills and learning from the human. Hopefully we will be able to get Ashimo to graduate. All right, well, I guess I'm going to stop here, and tonight we will see the rest of the group. Yesterday we had a session, very nice session. We will talk about the final, and those who I won't see tonight, well, I wish you good luck for the final, and for those I will see, we will talk about it more in the evening. So 7 o'clock. Okay, stop here.